It's a great pleasure for me this morning to introduce Prof. Michele Dougherty, who is a distinguished scientist, to say the least. She obtained a PhD at the then University of Natal in 1989 for research on wave particle interactions. She left South Africa for a fellowship in Germany, then moved to Imperial College London in 1991, where she was appointed professor of space physics in 2004. She is now head of Department of Physics at Imperial College. She is principal investigator for two major space missions, the NASA Cassini spacecraft and the ESA spacecraft. She has had many honors. Amongst them are, she's a fellow of the Royal Society, awarded the Royal Astronomical Society Geophysics Gold Medal in 2017, and made a CBE in the 2018 US Honours List for services to UK physical science research, which is a very top honor. She won the Institute of Physics Richard Glazebrook Gold Medal and prize in 2019. So very distinguished, and it's a great honor, pleasure for me to introduce her. And the title of her talk is Cassini-Huygens Mission to Saturn and its Moons. Thank you, Michele, please.
Hazel, thank you very much. I often don't recognize myself when I'm introduced, but thank you very much. So yes, it's a great pleasure to be with you today, and I'm excited to describe to you some of the work that I do. And I'm going to start off with, I think, my favorite image from the Cassini-Huygens spacecraft. And that is one that was put together from lots of different pictures that were taken by the camera on board Cassini over a long period of time. And as you can see, it's essentially put together an image of the entire Saturn system. And so you can see Saturn with the sun glowing behind it. And you can see some sunlight just peeping out from the south pole of Saturn. You can also very clearly see the solid rings of Saturn, where if you look at them in the night sky with a telescope, you can see those rings. But you can also see a new ring called the E ring, which is a very diffuse ring that you can't see with the naked eye unless you get really close to Saturn. And this is something I'm going to talk to you about later. It's a discovery that my team made. What we discovered, and you can see there's a little moon embedded within this E ring called Enceladus. And what we discovered is that this moon is actually outgassing water vapor, and you can see one of the water vapor plumes very clearly with the mouse that I'm showing there. And so that was one of the major discoveries, and it made us think that this is a place where life could potentially form, but I'll talk to you about that in a bit more detail as we go through. And then last but not least, and I think this is why this is my favorite image, where my mouse is now is the Earth. And so even looking at it now, the hair on my arm stands up on end, because there we were way out at Saturn, taking pictures of Saturn, and we could see the Earth all the way from that distance there. Perfect. Okay. So this view here, I just wanted to give you an idea about it, what our thoughts of Saturn were. So the first observations that were made from the Earth were made by Galileo way back in 1610, and he had a very small telescope. And these are the pictures he drew as a result of looking through his telescope. And it was really weird to him, because what he saw seemed to change every time he looked. And it was only when, with a better telescope 45 years later, that Christian Huygens realized that these funny arms that were being seen at the side of the planet was actually a set of rings. And Huygens also discovered Titan in the same year. Oh, good, it's working properly. And so what Huygens realized, and you can see Huygens' sketch of Saturn in the upper top left-hand corner there, is what he realized is that Saturn has an inclination on its axis. And so as it's orbiting around the sun, you can sometimes see it sideways on, and other times it's at a big angle to you. And if it's sideways on, because the rings are so small and thin, you can't actually see them. So that was why for quite a long period of time, they didn't quite understand what they were seeing at Saturn. And so something else that happened is Cassini actually discovered there was this gap. You can see this black line that he drew, this gap between the rings. And in fact, it's a bigger gap than it looks there, because when the Cassini spacecraft first arrived at Saturn, we actually flew up between this large gap between the rings. So one of the notes I wanted to make is that if you are involved in a spacecraft mission as large as Cassini, you really need a huge amount of international involvement, because it's not only is it expensive, but also it takes a long time to build. And I think for me, the thing I appreciated most about my involvement in Cassini was how all the scientists and engineers from all the different countries around the world worked together so well to get the fantastic results that we did. But this shows you all the different countries that were involved. And on my team, I had scientists from the UK, from Germany, from Hungary, and from the United States as well. Now, this shows you a nice view of the spacecraft. You can see it's covered with a lot of gold foil. And this gold foil acts as a thermal blanket. It helps keep the instruments in the spacecraft at the kind of temperature where they can operate. My instrument is a magnetometer, and what it does is it measures the magnetic field. And what we do is we put it on this very long boom here, because we want to try and get it as far away from the spacecraft as we can. So the magnetic field we measure is due to the environment we're in and not due to the spacecraft. So we have two different sensors, and I'll show you those shortly. One of them halfway down the boom where my mouse is, and then one right at the end of the boom as well. And then last but not least, let me point out to you this white umbrella-shaped object. That was the high-gain antenna. And once a day, the spacecraft would turn and point down at the Earth and send data back over an 8-hour period. And I did say last but not least, but one final thing I want to point out to you here. This probe here was the Huygens probe. And this was built by the European Space Agency, and it actually traveled down through the atmosphere of Titan. And I will talk a little bit about that too. This view here shows you the spacecraft before it was launched in a test chamber, where it was tested to make sure that it and the instruments on board could survive the vacuum of space, but also survive the vast temperature range that they would see. I'll show you the route that we took to get to Saturn. We flew past Venus a couple of times, and then some of the other planets in the solar system before we got to Saturn. And so the temperature range that we saw was from plus 40 degrees at Venus to minus 170 degrees at Saturn. And so we needed to make sure that everything could operate at those temperatures. I also like to show this because you can see how large the spacecraft is. Here is a person standing in the test chamber. And one final thing that you might notice is the boom that my instrument was placed in is not there at the moment. And if you think about it, you can't launch a spacecraft with a long boom, an 11-meter boom, sticking off from the side of the spacecraft. So what happened is we folded this boom away into this canister here, and the boom was deployed, in fact, when we flew past the Earth. So I said I'd show you the instruments. It was two different instruments, as I mentioned. The one on the left is a flux gate magnetometer, and that was built at Imperial College. And it's a very similar instrument to what we're building for the mission that's going to go to Jupiter, which I'm going to refer to towards the end. And on the right is another type of magnetometer called the vector helium scalar magnetometer. And this was in fact built by our colleagues at the Jet Propulsion Lab in California. And in fact, it stopped working about a year after we got to Saturn, which made the calibration of our instrument quite complex. But I can describe that to you later if any of you would like to ask me any questions about that. So this is how we went to Saturn. So what we're doing is we're looking down on the solar system. We have the sun. Where's my mouse? Here it is. We have the sun there. We have Venus, the orbit of Venus here. The orbit of the Earth just here, and then Jupiter and Saturn fall further out. Now, we don't have any rockets just yet that can launch a spacecraft as large as Cassini with enough energy to get straight out to Saturn. So what we do is we use flybys past other planets. And the way I like to think about it is it's a little bit like a billiard ball, or two sort of billiard balls, or pool balls on a pool table. If you have one stationary one and one moving one, if the moving one bumps into the stationary one, it'll give a little bit of energy to the stationary one and get it to move. And that's essentially what planetary flybys are like. We get within the gravitational field of that planet, we gain some energy from it, and it then gives us a further kick to get further on our route out to Saturn. So we were launched on the 15th of October, 1997. We had 2 flybys of Venus. a flyby of the Earth when we deployed the magnetometer boom and turned the instrument on to make sure all was well. We had a flyby past Jupiter, and then we finally reached Saturn in 2004. And just looking at that timeline, you'll see that one of the things you need if you're involved in outer planetary spacecraft missions is lots of patience, because it takes a very long time from your first idea about flying a particular mission to actually getting there and taking the data. So let me talk, I want to talk really about two different moons, and then I'm going to talk about the end of mission for Cassini. And the first moon I wanted to talk about is Titan. Now, this is the view that we had of Titan from the Hubble Space Telescope before Cassini got there. It's the largest of Saturn's satellites, and it's the only one in our solar system that's known to have a dense atmosphere. And you can actually see the atmosphere in blue in the bottom right-hand image there. Now, Hubble Space Telescope had not been able to see through this haze. And so there was this orange hydrocarbon haze that essentially masked the surface. The reason that we wanted to look more closely at Titan is we thought, and it is now true, we know it's true, that the chemistry of its atmosphere is very similar to what the Earth's atmosphere was like when it first formed. And so it's almost like a way of going back in time for us, having a look at Titan's atmosphere, allowing us to then better understand how our atmosphere evolved over time. And so what we did is we used the Cassini spacecraft to fly past Titan about 120 times by the end of the mission. But we also had the European Huygens probe actually traveling down through the atmosphere of Titan and landing on the surface. And there were some nice images that were shown at the time of what the surface looked like. But for me, I think one of the great discoveries was the fact that we found liquid on the surface of Titan. But I've jumped ahead of myself. Let me just show you this, talk to this image here. This is a view that was taken by the camera on board Cassini. And because we were so much closer, you can see there are some hints of some surface features. But again, this visual camera was unable to properly see through the haze. And so we had to use some of the other instruments on board Cassini to be able to do that. And this is data from one of the other instruments. And this was taken by the visual infrared mapping spectrometer. So it was an instrument that viewed in the infrared wavelengths and was actually able to see through the haze. But one of the biggest surprises when we first got there was for the first 4 years that we were in orbit, we couldn't see any liquid on the surface at all. And the Huygens probe, as it traveled down through the atmosphere and landed on the surface, showed us what looked like lakes and river features. And so we were almost certain that there was liquid on the surface, but we didn't see it. And then eventually in 2009, so 5 years after we got there, the VIMS instrument caught this glint of sunlight at the North Pole. And this flash of sunlight was being reflected off a lake on Titan at the North Pole. And this was the first confirmation that we had that there was actually liquid on the surface. And the reason we hadn't seen it before was because of the seasons on Titan. Prior to that, the northern hemisphere of Titan had been in winter darkness. And it was only when the sun began to illuminate the North Pole that we were able to see this glint. And following this observation, we have now had many observations of liquid ethane and liquid methane on the surface. There is also liquid water, but it's not on the surface. It's in the interior. It's underneath the surface. And so Titan is a very strange place. This here shows 6 infrared images, again from the same instrument that I talked about in the previous slide, which was essentially a concatenation of 13 years worth of data. And it gives you now a view of the surface of Titan. This, in the third right here, this blue, icy blue region, or blue-gray region rather, this was called Xanadu, and this was the only surface feature that had been glimpsed through the haze by the Hubble Space Telescope. There are other interesting features. There's an ice volcano, which I'm pointing out with my mouse there. We have these purple regions that you can see. That is frozen water ice. You can also see these brown regions. These are sand dunes, which essentially seem to cover most of the equatorial region. And so we now have a much better understanding of Titan. And in fact, there's a lot of interest in going back to Titan in the future. And NASA is planning a mission called Dragonfly, which is going to go back to Titan. So let me move now on to maybe my favorite moon in the Saturn system. But before I do that, I just wanted to talk very briefly about the measurements that my instrument makes. So I mentioned to you earlier, the instrument measures the magnetic field. You can't see a magnetic field, but if you have the right instrument, you can measure it. And this shows a view of the Earth where we know there is a magnetic field on the Earth. If you stand on the surface of the Earth with a compass, the needle of that compass will point to the North Pole of the Earth's field. If we were able to see what it looked like, it would look like these red lines that you see. And one way of thinking about it is, it's almost, let me take a step back. If you have a piece of paper, you put a bar magnet underneath that piece of paper, and you put iron filings on top of the piece of paper. Those iron filings are going to lie along the lines of force of the magnet. And that's essentially what my instrument measures. And so for a lot of planets in our solar system, you essentially have equivalent of a magnet in the deep interior. It's called the planetary dynamo. And what that does is it generates the magnetic field that you can measure outside. So that's what my instrument measures. We have a similar magnetic field at Saturn. One final point I want to make on this slide, and I want you to remember that as we go through the discovery that we made, is that Saturn, just like the Earth, orbits once a day on its axis. And as the planet rotates, these magnetic field lines are going to rotate at the same rate. So if we're on a moon where my mouse is, say, those field lines are going to be passing over the moon. And that's partly linked to the data I'm going to show you next. So let's just remind ourselves about the Saturn system. We've got Saturn in the top left. We've got the visible rings that we can clearly see. We've got the moons at different distances orbiting around Saturn. And we've got this E-ring that I pointed out to you right at the start, the very diffuse ring. And embedded within this E-ring is the moon called Enceladus. Now, the E-ring is made up mainly of water ice, and Enceladus at its orbit, you can see it's orbiting outside of Mimas, one of the other moons, and inside of Tethys. And that's something I want you to keep in mind when I show you the data. So this is the view that we had of Enceladus from the camera on board Cassini. And one of the things that you'll notice is there are some cracks on the surface, but there are hardly any craters at all. And that was a real surprise for us because, let me go back. These two moons, where's my mouse gone? It's got a mind of its own today. These two moons, Mimas and Tethys, their surface are covered in craters, but Enceladus doesn't seem to have any craters on the surface. And so the implication seems to be that something is happening at Enceladus. Something is making the surface much younger than we thought it would be. And because it's embedded within the E-ring, it had long been thought that maybe it's somehow the source of the E-ring, but no one quite understood how that could be. So the plan was, and this was in 2005, we had 3 flybys of Enceladus planned by the Cassini spacecraft. And that the distance away from the surface of Enceladus is shown in brackets at the bottom there. So the first one was quite a distant flyby. We then had another one a month later, which was closer. It was only 500 kilometers away. And then the third one, which was 4 months later, was originally planned to be 1,000 kilometers away from the surface. But based on the observations that my instrument and my team made, we were able to persuade the Cassini project to take us much closer. So let me show you those observations. So you have to be a magnetometer person to get excited by looking at magnetometer data, but let me just talk you through it briefly. I won't spend a lot of time on this, I promise. So a magnetic field is a vector. So that means the way that you can describe it is there are 3 components, these 3 components here, and then the magnitude of the field is shown down below. And what I'm showing you here is 24 hours worth of data. And the Enceladus flyby was here. So looking at how the data is behaving, it seems to be doing something like that, and then something happens as we fly past Enceladus. Looking at this component here, it's quite a strong field if you compare it to the one above, but there seems to be a little pimple in the data just there. Something really weird was taking place in this component, and then in the magnitude of the field, so the strength of the field, again, there's this little pimple. So what we did is, to make it easier for non-magnetic field experts to understand, this is what we did. We subtracted the magnetic field of Saturn away from the data, and we were left with only that due to Enceladus. So this is another view. What we're doing now is we're looking down on the north pole of Enceladus. Saturn is way off the top of the page. This is the trajectory of the spacecraft. So this is the motion the spacecraft made. And overlaying on top of the spacecraft trajectory are these little field lines. And this is what the magnetic field, we think, due to Enceladus was doing. So what seemed to be happening is it was almost as if Enceladus was a much bigger obstacle than it actually is. Something was stopping the magnetic field from pointing towards and penetrating down onto the surface. And in addition to that, we had a lot of wave activity in our data, and we were able to look at the data, and what it was telling us is there was a large increase in water group ions as we flew close to Enceladus. So based on data from the first flyby and very similar data from the second flyby, this is what we put together. This is what we thought was going on. So our eyes are looking down on the north pole of Saturn. So here's the north pole of Saturn. The gold rings are the visible rings of Saturn. The blue lines are the magnetic field lines of Saturn, which are orbiting with the planet once a day. And Enceladus, the little orange ball, is orbiting around Saturn as well. Now, if Enceladus was a dead body, the magnetic field lines of Saturn simply wouldn't see it. And they would move through Enceladus, just as you can see in that little movie there. What we seem to be seeing, though, was something different. So now we're looking sideways on Enceladus. So here's my mouse gone. Here's Enceladus. Here are the magnetic field lines of Saturn moving towards Enceladus, and something was stopping them from penetrating down onto the surface of Enceladus. And one way in which you can do that is if you have an atmosphere, just like we have at the Earth, because what happens is the upper regions of the atmosphere become ionized from solar radiation, and it stops the magnetic field of the sun, or in this case of Saturn, penetrating down onto the surface. And it actually protects us. On the Earth, it does. It protects us from the effects of the energetic particles from the sun. So what I did is I put together this schematic here, which showed a diffuse atmosphere covering the entire surface of Enceladus. And I actually went out to the Jet Propulsion Lab, and I gave a presentation to the project at the Jet Propulsion Lab. And what I was trying to do is I was trying to persuade them that we thought we were seeing an atmosphere at Enceladus. And what I wanted to persuade them to do was, on, as I mentioned earlier, the third flyby planned 3 months after those first two, I wanted us to fly much closer to see if we could see something. And I was a little bit nervous because, you know, we had spent 6 years planning all the observations we were going to make, and changing at this very late stage was something I was concerned they wouldn't be prepared to do. But I remember I was very jet lagged. I'd only got in the day before, and I was standing in a line at Starbucks waiting to buy some coffee. And the man standing in the line in front of me turned around, and it was the guy who was responsible for the spacecraft. And he said, "Hey, Michele, what are you doing here? I didn't know you were here." And I explained to him, and his eyes lit up, and he rubbed his hands together in glee, and he said, "I've always wanted to go closer to a planetary body than anybody else." And so going into the meeting, I knew I had at least one person on my side. It was a difficult sell to make, but eventually we agreed that the observations that we had seen were interesting enough and could be really groundbreaking. And so we needed to go much closer on the third flyby. So what the project did is they planned the flyby, and they planned to fly just below the South Pole. And that was because that was the easiest way to do it. It would use the least amount of fuel, rocket fuel, to do that. And this was very fortuitous, because what we found on that third flyby was that instead of the atmosphere covering the entire surface, it was focused at the South Pole. It was almost like a cometary jet of water vapor coming out from the South Pole. And so we essentially flew right through this plume here, 173 kilometers above the surface. Now, because we went so close, all of the other instruments on board the spacecraft were able to take really fantastic data as well. So I want to show you some of that data. So this is data from two different instruments. The first one is from the visual camera. So this is in the top left. And what you can see is at the South Pole, there are these deep fractures, or what that team called tiger stripes near the South Pole. If we combine that with another data set, and this is data from an instrument which is able to remotely sense the temperature on the surface. So what we thought we would see is that the hottest region would be at the equator, where the solar radiation is strongest. And we did actually see it was rather hot there. But the real surprise was there was this huge hotspot right at the South Pole. And if you overlay these two data sets together, the hottest spot was right on top of one of the cracks. And so the implication was that, really surprisingly, Enceladus, which is a very small moon, it's only 500 kilometers in diameter, had internal heat. And this internal heat was leaking out through these cracks on the surface in the same region that water vapor was leaking out from underneath the surface as well. We really didn't expect this. We had long thought that Enceladus had cooled down from when it first formed. So this was a real surprise. This here shows you a view again from the imaging camera on board. This was actually a few months later, it turned its camera back to look at Enceladus. And you can see how large this water vapor plume is. And there's not only water vapor in it, there's a lot of dust material as well. And these different colors show you the different densities, but you can also see it almost looks as if they're different sources. And so, you know, there's water vapor coming out of a crack just about here, and there's water vapor coming out of a crack here. And these different these cracks seem to open and close over time. And so it was a very complex process that was taking place. But for me, the real important observation, combined with everything else that we saw, was made by an instrument called the ion neutral mass spectrometer. And what this instrument was built to do was essentially taste what we flew through. And so as we flew through the plume, it saw there was water vapor in the plume, but we knew that anyway because my data had shown that. There was also methane, there was carbon dioxide and carbon monoxide. But the real discovery was the fact that there was simple organic material and complex organic material as well. And this is when we began to think that Enceladus might be a place where the ingredients could be there, that life could potentially form. You need there to be the following things. You need there to be a source of liquid water, and we know it in Enceladus. There's liquid water underneath the surface. You need there to be a heat source, which we also know is there. And you need organic material, which we now see is there as well. The fourth thing you need is for those first three ingredients to be stable enough over a long enough period of time that something can actually happen. And so this was the first time that we realized that way in the outer solar system, at the orbit of Saturn, there might potentially be the ingredients for life to be able to form. Now, I just want to step back and talk a bit about Jupiter. I will, at the end of the presentation, I'll talk about the Cassini end of mission. But the reason I wanted to talk a bit about Jupiter is linked to the fact that I led a team which put a proposal together to make a case to the European Space Agency that we should fly a mission to Jupiter. And in fact, the discoveries we made in Enceladus really helped us make our case. So this pretty but rather complicated looking diagram, let me talk you through it. So what we're looking at is we're looking at the fact that it's now a commonly accepted fact that there are two habitable domains in every stellar system, in every system around the stars that we have. There's this very narrow one here, where any water that you have in liquid form can be on the surface, just like we have at the Earth. And the position of this domain here is actually driven by temperature variations away from the star. And so what that imposes is the surface habitats, if they exist, must be quite close to the star. But what we've learned in the last 30 years, and for me, that's the most important thing we've learned in planetary science, is the fact that there's a much larger habitable domain. There's this dark blue domain here, a zone where water is very abundant, but it's not found on the surface. You find liquid water in deep reservoirs or oceans underneath the surface. And this second domain is beyond the snow line, which is this yellow dotted line that you can see here. And we think that in this domain, water is as abundant as silicates are in the surface habitats domain. Now, the Jupiter system is in this domain, and so we were able to use this fact to persuade the European Space Agency to allow us to plan, and we're now in the midst of finalizing the instruments for the JUICE spacecraft mission. And what this JUICE mission is going to do is it's going to focus on 3 of the moons. It's going to focus on Europa, which is this little moon to the left, and we think Europa is very Earth-like. And it's also going to focus on Ganymede in the middle and Callisto on the right. And Ganymede and Callisto have got liquid water underneath their surfaces, and they're the type of body which are known as water worlds. And in fact, we think that the exoplanets that keep getting discovered have got many moons in orbit around them which are water worlds. And so by focusing on Ganymede and Callisto, we will get a much better understanding of these water worlds and help us better understand some of the exoplanet work that is going on as well. And so some of the plans that we made have been based on some of the observations that were made by the NASA Galileo spacecraft back in the 1990s. And these show the interior structures of 4 of the large moons of Jupiter. And the ones that we're going to focus on are Europa, where there's a liquid ocean underneath the surface, but we think it's quite close to the surface. And then Ganymede, bottom left, where again, there's this liquid water ocean, and Callisto as well. So that's going to be our focus. And this gives you a view of the spacecraft. We're going to, for the first time, be using solar panels as our power source. And so you can see these artist's impression of these large solar panels at the spacecraft. And Jupiter is about as far as you can go in the solar system where solar power can be used, because if you go beyond that, the solar power begins to drop off quite quickly. And so you really don't have enough power to be able to drive all of the instruments. Now, the plan is that we launch to go to Jupiter next year. It's been rather difficult the last couple of years because of COVID lockdowns. And I think the thing that I'm most proud of in the last 18 months is the fact that my engineering team has been able to build an instrument in lockdown. And so these are some pictures of the instrument itself. So let me show them to you. Where my mouse is now, that's the electronics box, which is on the main body of the spacecraft itself. And we have 3 different instruments. We have the one built, I keep losing my mouse, sorry. Where my mouse is now, that's the one built at Imperial College, just down the corridor from me. This one here is built by some of my team who are based in Germany. And last but not least is the instrument which is going to be right at the end of the spacecraft boom, which is built in Austria. And the other 2 pictures show you various tests that were done to make sure that our instrument will be able to survive the rigors of launch and the rigors of space. The bottom left-hand one shows you the electronics box on a vibration table where we vibrate the table very rapidly, which is what would happen when launch occurs. And we test to make sure that the box survives. And then there's one on the right here is always a scary one for me. There's a large hammer, which I'm pointing out with my arrow there, and that's dropped on the box. to make sure that it can survive the impact of the hammer. So it's always a bit nerve-wracking when the instrument is put through all these tests. But for me, this is something that is really something to be proud of. Some of my engineers were actually building the instrument on their kitchen table in the midst of lockdown. Although we were lucky enough that Imperial College allowed us to slowly start reopening our research labs in the department in June of last year. So slowly but surely, people were able to come back and continue to focus on building in the lab itself. So in the last 10 minutes or so, what I'd like to do is talk about the end of mission for the Cassini spacecraft. Now, originally Cassini was only due to spend 4 years orbiting around Saturn, but we had more than enough fuel to keep going. The spacecraft was in good health, and all the instruments were in good health as well. So we kept extending the lifetime of the mission. And by the end of the mission, it had lasted for 13 years in orbit. But it was very clear to us that we were slowly running out of fuel. And the decision that we had to make was, how did we want to end the mission? And what we decided we wanted to do was we wanted to get as close to Saturn as we can. Now, I haven't had time to talk about this today, but one of the real surprises at Saturn is that we don't understand the magnetic field that is generated in the deep interior. It's very different to the magnetic field we see at Jupiter, and it's very different to the magnetic field we see at the Earth. And so what we thought was that if we can, and I'll my mouse again, if we can get inside the rings, because we thought the rings might be masking the effect from the deep interior. If we could get deep inside the rings and make observations deep inside the rings, that might then allow us to get an understanding about what the magnetic field really was like. And so this essentially shows you the last year of the mission. We used Titan. This green circle shows you the orbit of Titan. We used the gravitational field of Titan to get the spacecraft up out of the equatorial plane. And we had 6 months of these gray orbits, which were known as the ring grazing orbits, where the closest approach was just beyond the edge of the visible rings. And we took a lot of data, allowing us to understand what it was we were observing as we got closer. And then we used Titan one final time to change the orbit once again to get us onto these pale blue orbits known as the grand finale orbits. And this got us closer to Saturn than we ever thought we were going to get. And in fact, we weren't planning to get that close. And so we had to persuade the Cassini project to allow us to roll the spacecraft when we were really close to the planet to help us calibrate our instrument, because otherwise we wouldn't have been able to make the science observations that we did. And then the last but not least, we've got this orange orbit, which is the final orbit. So let me talk you through some of what we saw. So this is actually a close-up view of the orbits. The blue orbits were about 3,000 kilometers above the cloud tops, and we kept getting closer and closer as the end of mission came upon us. And each of these flybys, we're doing a close flyby of Saturn every 6.5 days. One of the reasons I like to show this is that you can clearly see that the visible rings of Saturn are not solid. They're made up of countless individual particles, each in their own orbit around Saturn. And so you can actually see the trajectory of the spacecraft through the rings. Now, what we wanted to do was as I mentioned a little earlier, we wanted to try and understand what the magnetic field of Saturn looked like. So, as I pointed out much earlier, these blue field lines that you can see here, that's what my instrument measures. And by measuring this magnetic field, it allows us to get an understanding about what's going on in the deep interior. We've always assumed the magnetic field is generated by something called dynamo action. And so it's a little bit like, it's a two-pronged process. You've got heat being given off, so it's a little bit like a porridge, but sort of almost bubbling on a stove. You've got this overturning motion that takes place, but you've also got the rotation of the planet too. And those two things combine to have the end result being that electrical currents flow within the interior. And those electrical currents generate a magnetic field. And we thought which is what we measure outside. And we thought if we got close enough, we'd be able to get really fine, detailed observations of this magnetic field and allow us to understand a little better what we were seeing. Now, this view shows you an artist's impression of the first very close flyby. And in fact, I went out to the Jet Propulsion Lab for this flyby because this was uncharted territory. We didn't know if the spacecraft would be able to survive this. We didn't know if this gap between the upper regions of the atmosphere of Saturn and the edge of the visible rings was clear, and whether the spacecraft would survive. And so that's why we went in the orientation that you can see there. The dives that we made had the high gain antenna, the yellow, the white umbrella shaped object pointing in the direction of travel, so that if we hit any energetic material, hopefully it would hit the high gain antenna and wouldn't destroy or damage any of the instruments or the spacecraft. So I bumped into the project manager just before we made this dive, and he was looking really nervous. And he looked at me and he said, "Oh, I'm really nervous about your instrument, Michele." And he reminded me, and I knew it anyway, of course, that my instrument was halfway down the boom and right at the end of the boom. So we weren't protected by the high gain antenna at all. So I must confess I was nervous before I saw him, but I was much more nervous after I'd seen him. But the spacecraft survived. It turned out there was a big empty gap. There was no energetic material in that gap. And so we were able to make 22 of these dives through this gap between the atmosphere of Saturn and the rings. This shows you a view from the infrared instrument that I showed you data from earlier. And this shows you the heat leaking out from the interior of Saturn. And that white ellipse-shaped object shows you where the spacecraft dove into the atmosphere of Saturn and burnt up. And let me just orient you better. It gives you an idea about where that region was. So it went into the atmosphere of Saturn just above the equatorial region, so just above the rings in the northern hemisphere. This here shows you a view from the mission operations room after Cassini had burnt up. And, you know, it was really interesting. Towards the end of the mission, we were doing these dives close to Saturn every 6.5 days, and we were exhausted. It was so exciting, but you just felt you couldn't keep up the energy for too much longer. And so part of me was actually relieved the mission was coming to an end. But then at the end of the mission, you suddenly realize that something you've spent 25 years of your life on is over. And for me, this image shows that really very well. But I think for me, the most poignant moment was this view here. So what this view shows, again, it's in the mission operations room. But what I want to point out to you is the data in the top left-hand view here. What this shows you is you've got the spacecraft talking to the Earth, and where you have the spike, it's telling you that the Earth and the spacecraft are talking to each other. And as the mission came to an end, that spike disappeared, and we thought it was over. And then it came back briefly before it disappeared for a final time. And that brief coming back was because the spacecraft hadn't been told its mission was over, and it had been trained to keep talking to the Earth. And so it fired its thrusters, and it kept, while it was beginning to break up, its main aim was to keep sending data back down to the Earth. So that's why we saw it continue to try to keep on talking to the Earth. And so to end, let me play this video for you.
A lone explorer on a mission to reveal the grandeur of Saturn, its rings and moons. After 20 years in space, NASA's Cassini spacecraft is running out of fuel. And so, to protect moons of Saturn that could have conditions suitable for life, a spectacular end has been planned for this long-lived traveler from Earth.
5, 4, 3, 2, 1. And liftoff of the Cassini spacecraft on a 1,000,000-mile trek to Saturn. We have cleared the tower. Its program is in. Full program is in.
In 2004, following a 7-year journey through the solar system, Cassini arrived at Saturn.
The SOI burn attitude or pointing position, light up the rockets.
The spacecraft carried a passenger, the European Huygens probe, the first human-made object to land on a world in the distant outer solar system.
Huygens arrival on Saturn's moon Titan.
For over a decade, Cassini has shared the wonders of Saturn and its family of icy moons, taking us to astounding worlds where methane rivers run to a methane sea, where jets of ice and gas are blasting material into space from a liquid water ocean that might harbor the ingredients for life. And Saturn, a giant world ruled by raging storms and delicate harmonies of gravity. Now, Cassini has one last daring assignment. Cassini's grand finale is a brand new adventure. 22 dives through the space between Saturn and its rings. As it repeatedly braves this unexplored region, Cassini seeks new insights about the origins of the rings and the nature of the planet's interior, closer to Saturn than ever before. On the final orbit, Cassini will plunge into Saturn, fighting to keep its antenna pointed at Earth as it transmits its farewell. In the skies of Saturn, the journey ends, as Cassini becomes part of the planet itself.
Thank you, Michele, for a very nice, exciting, and thought-provoking presentation. And what goes beyond. I mean, there's so much more. It's amazing. I mean, it opened up everybody now, I think, and there's, I'm sure there are questions, and I'll open up. Andre has got his hand up. Can you unmute, please, and ask your question?
Hi, Michele. My name is Andre Strydom. I'm from the physics department at University of Johannesburg.
Hello, Andre.
My thanks for an absolutely fascinating talk. I believe I saw this grand finale on one of the television channels not long ago, and I recorded the event. It was just so fascinating. I have two questions. The first question, if you could please page back to those magnetic field measurements upon the pass-by of Enceladus.
Of course.
That series of arrows that you had there.
Okay, I'm sorry, everyone. I'm going to make you seasick by moving quickly, but I don't want to try and do it any different way. So
no problem.
That one there, Andre.
That one.
Okay, perfect.
So my first question is, could you comment? Looking at the arrows and imagining where Saturn might have been during the collection of those arrows, yes. I couldn't help but thinking, and especially looking at the upper left corner, I couldn't help but thinking there seems to be a third source of magnetism, aside from Enceladus and aside from Saturn. That's my first question. And if I can go right on to my second question, was whether you were able to detect time variation in magnetic field, or to put that in a different way, what was the time rate of field measurements that you did, to give an idea of whether there were any pulsing magnetic fields present or not?
Do you mind if I move to the previous slide? talk you through the actual data itself, and then we can come back to this one if you like. So the data that you're seeing here, our time cadence for the data was, we could take as high as 24 vectors a second. But what you're seeing here is 1 second average data. And some of, I mentioned that we had a lot of wave activity in the data. You can see it here where my arrow is. You can't see it, of course, in the second component because it's so strong. But you can see the waves that I was talking about in the data, both before and after the flyby, and those were the gyro frequencies we would be able to resolve and then work out it was water group ions doing it. As far as your question about there being a third source, these arrows here are partly linked to the fact that Enceladus and the E-ring is embedded in this current sheet at Saturn. So the magnetic field lines of Saturn above the equatorial region, you've essentially got this plasma sheet. So the field is pointing in one direction above it and in another direction below it. And here we were above the current sheet. And so these vectors that you're seeing here is essentially telling us that we were above the current sheet. So I don't think there's well, yes, I suppose there is a third source in a sense. It's because we're embedded within the current sheet or the plasma sheet at Saturn. Does that answer your question?
That helps to understand. I mean, if the sheet that you're talking about, if there could be either moving sources of gravity or moving sources of charge, that would immediately give you a possibility of magnetic field.
Absolutely, and that's one of the complications at both Saturn and Jupiter, is when we're looking at the moon flybys, and it's one of the things I'm losing sleep over about the Jupiter data that we need to take. But we have these plasma currents flowing, and they generate fields of their own. They generate magnetic fields of their own, and they're time varying. And for me, I think the most difficult observation we're going to need to make at Ganymede is we're going to have to separate all these time varying fields out, because what we're trying to resolve are the induced currents that are flowing in the liquid water ocean. So the way I describe it, it's like trying to find needles in a haystack, but the needles are changing shape and color all the time. So that's what I lose sleep over.
Got it. Thank you very much.
Of course.
Thank you for that. And I've got another question. Is Abdul Hamid Kara? Please, could you unmute and ask your question?
Hi, Michele. Hi, Faisal. It was nice. Your talk was a very good talk. I attended your last one when you were at WITS.
Oh, okay, cool. Nice to see you again then.
Yeah, that was coinciding your visit to the SAMS Congress at the time, if I'm not mistaken.
That's right, yes. Yes, I can't wait to be able to travel back to South Africa. I really can't.
Yeah, well, we'll wait for you too. Interestingly, I was driving past on Sunday, past Mikey's Fontaine, you might know that, which is, of course, a turning point to Sutherland.
Yes.
Sutherland is known for the telescopes. Okay, so my question is the following. So many years ago, I read Broca's Brain, Carl Sagan's classic book, and he spent a whole chapter speaking about Titan being the most likely candidate for future occupation.
Yes.
Because of its conditions being close to Earth and so on. Has that idea now been abandoned in place of Ganymede and Callisto and so on?
No, it certainly hasn't. It's just another place to go. So from my perspective, and I think I alluded to this when I moved from talking about Enceladus to talking about the JUICE spacecraft. I think that's one of the biggest discoveries that's been made in the last 35 years, is the fact that there are now numerous places in the outer solar system where there is liquid water, and where we think there's the potential for habitability. You know, I'm always very careful when I describe this, and when we made the case to the European Space Agency to have the mission to Jupiter, I don't like saying we're going to search for life, because that's a step too far at this stage. What I do say, though, is what we want to do is we want to understand whether the ingredients are there for life. And so what we're looking for is potential habitability. So for me, the places in the solar system right now are at Jupiter, in the outer solar system, sorry. At Jupiter is Europa, Ganymede, and Callisto, and probably in that order. And in the Saturn system, it's difficult to know Titan or Enceladus. They've both got liquid water underneath the surface. Titan, we're planning to go back to. Enceladus is more difficult to go back to because it's so small, its gravitational field is small. We need a huge amount of fuel to be able to go into orbit. And so I think it's going to be some time before we can go back to Enceladus. But then we mustn't forget the real outer solar system, the moons of Uranus and Neptune as well. But that's going to take a very long time to be able to get there. So that's why we're planning to focus on Jupiter and Saturn at the moment.
Well, at least for now, when you mentioned the moons of Jupiter, I got a bit excited. You can actually go out with your binoculars and watch some of those moons. Absolutely. And maybe you can see someone fly in.
Well, in fact, you know, I have to pinch myself that I ended up working in Planetary spacecraft, because when I was a kid in South Africa, in Durban, my dad built his own telescope. He ground the mirror of the telescope. And my sister and I were so proud of ourselves because we mixed the concrete for the base of the telescope. And my first view of Jupiter and its moons and my first view of Saturn and its rings was through the telescope that my dad built. And here I am 40 years later working on these moons. And it's crazy. It's really crazy.
Well, just a quick last comment. When you mentioned about your dad building a telescope, just the other day I had a chat with the head of the chemistry here, Wits,
yes,
who's also into watching the skies and so on. And his dad built a telescope, and that's what he's using right now to watch the sky.
Yeah, no, I think my dad's telescope ended up at one of the schools in Durban, actually. So yeah, that's where it is at the moment.
Thank you very much for the nice talk.
Of course, thank you.
Okay, thank you. And now we've got Tama Duba to ask a question or make a comment. Please unmute and ask.
Yeah, thank you so much, Prof. Michele, for a lovely talk. I was intrigued by, there was a slide, I didn't pick up what page it is.
Mm-hmm.
You were showing the interaction of the magnetic field and rotation.
Okay, and nice to hear you, Thomas. Sorry, I can't see you, but nice to hear you. Was it the one that showed the Earth? That one?
I can't remember. I just remember you spoke about the interaction between the magnetic field and the rotation. And I wanted to find out what kind of an impact that interaction had on your spacecraft.
Are you thinking about when I was talking about the interior of Saturn, where the magnetic field is generated? Let me move. Sorry, I'm going to make you guys seasick again. Let's have a look. Where I was talking about this one here, the bottom right is
yes, that this one.
Okay. What was going on in the interior, the way in which it impacted the spacecraft is what goes on in the interior generates the magnetic field we see outside.
Okay.
And so the way in which it would have an impact on the spacecraft is if there are any intense radiation belts, because there you have to be really careful. At Jupiter, we have to be really careful. We don't want to go too close to Jupiter because they're very intense radiation belts. Whereas at Saturn, there isn't the same intensity of the radiation belts. But, you know, I'm glad you asked the question, Tama, because I'm going to take this opportunity just to talk a little bit about why we were so surprised about what we saw at Saturn. Our understanding of planetary dynamos, our understanding has always been that the rotation axis of the planet and the magnetic dipole axis, there's always a tilt between them. At the Earth, it's about 22 degrees. At Jupiter, it's just under 10 degrees. At Saturn, all the way through the Cassini mission, every time we looked at more data, the tilt got smaller and smaller. And we didn't understand that. How could the magnetic field be generated without there being this tilt? And so that's why we thought if we got really close, if we got inside of the rings, we'd be able to see the tilt. But in fact, inside of the rings, the tilt got even smaller. So the tilt is 0.00007 degrees, which effectively means it's not there. And what we think is happening, and this is really unique in the solar system, is we think that the planetary dynamo process in the interior is happening as we would expect it to, but that there's a second dynamo region much closer to the surface, which is masking the effect of what's going on in the interior. And we've got planetary dynamo colleagues trying to model this at the moment. So, you know, I kept saying, as we were approaching the end of the mission, I kept saying, give me another 6 months and I'll find you the tilt. And I never found the tilt. I found it wasn't there, but it's a result, I suppose.
Okay. All right. I'll allow other students to ask.
Okay. Nice to talk to you.
Thank you.
Thank you. We got one more question, I think. Oliver Going, Palace Singh. Please unmute and ask.
Hi, everyone.
Hello.
An amazing presentation, by the way. So,
thank you.
I would like to ask, based on the current exploration of the exoplanets and others, if everything goes well and you find that there are the ingredients you're looking for, that you find habitability in certain planets, then from there, what's next for those planets? Will there be further exploration of life? Will there be, what will be the further missions after this one may be accomplished?
That's a very good question, and I think I'd like to focus it more on our solar system, just in the sense that for the exoplanet missions that we have at the moment, they are remote sensing missions. And so they will be put into orbit around the Earth. They'll be above the atmosphere, but we'll have to remotely sense what's going on at the exoplanets. But in our own solar system, we can actually physically go there. And so I think, you know, scientists always get so excited and they say, oh, let's go to Jupiter's moons now and take a lander. And I asked the question, where do we land? Which moon do we land on? And if we land on Europa, where do we decide to land? We need to know where we want to land. And so that's what JUICE is going to do for us. But there's not only the JUICE spacecraft, which is being run by the European Space Agency, there's a NASA spacecraft mission called Europa Clipper. And that's going to be a spacecraft that's going to essentially fly past Europa many, many times. And so what we want to do is we want to use those two missions to essentially work out where the ice crust at Europa and at Ganymede is thinnest. Because if we want to see whether there is organic material at both of those moons, we need to get underneath the surface. And so we need to know where to land. And so for me, the next step would probably be after Europa Clipper and after JUICE, we would send a lander mission and we would know where to land, so we could get underneath the surface. So, you know, it's a sort of, you need lots of patience, and I'm not renowned for my patience, but it's a step-by-step process. You need to know where to focus on.
Yes, that's definitely true. I understand. Thank you. Thank you.
Fario, please, you want to go ahead and ask?
Yeah, thank you, Prof. And I came a bit late, and I'm very sad about that. But I have a question. Mars is much closer to us than the mission you've been involved in.
Yes.
And I understand that even to get to Mars, there has been a lot of miss. You know, I mean, when humans sent satellites to the planet Mars, there have been many missions that were unsuccessful. Yet, the planet we are working on is much further away. So how does one get it right that one does not miss, you know, landing on this planet? I don't know if you understand my question.
I do. And I think it's partly linked to how much money and time and effort is put in. When planetary exploration first started, there was a real focus on success. We have to make sure that it works. And the large planetary missions like the Galileo mission to Jupiter and the Cassini mission to Saturn, they were known as flagships. in that a huge amount of money and effort was poured into them to make sure that they worked. On some of the missions that went to Mars, they were known as fast and cheap ones. And so let's see if we can do science cheaper and much more quickly than we do on the large flagship, but know that there's the chance of them not actually working. And I think that's partly what we were seeing at Mars. We were testing out new technology that maybe we weren't sure was going to work. And so it's essentially a mix of let's see how quickly we can do this and how cheaply we can do it versus let's spend a lot of money and make sure that we get it right. And so it's a bit of a mix. I think probably the best way to do it is somewhere in between. But particularly for missions where it takes us 7 or 8 years to get there, you really want to make sure that you get it right. And I think that's why the focus has been on taking longer to prepare for the missions in the outer solar system.
I see. Thank you.